So we're going to continue today with the topic of multiple sequence alignment, which Michal has introduced to us this morning. And we're going to see how we can use BioPython to do pairwise alignment. But before that, we will actually begin with a different topic of error handling. And we're going to speak about stack traces, exceptions, the syntax of try, except, finally, etc. We'll see how we can raise exception, assert with all of that. So that will be the first topic that we cover today. So let's go right ahead to the notebook, which is called, I think, error handling, this one. Okay. So some setups. So I first want to say a few words about this thing which is called stack traces. So suppose that we have some code like you see here, and we execute it. And then we get this output, which I suppose that by now we are all very familiar with it. Saying that you did something wrong and you get this error. So I want to spend a few minutes on that and trying to distill exactly what we see here and what's the meaning of all of these outputs. So the thing that you see here is called a stack trace or a traceback. And it actually tells you most recent call last. We will soon see exactly what it means. The most important part, of course, is the end of it, where you see the type of the error that you get, and then the message of the error. In this case, it's quite straightforward. What you see is a zero division error, and it says the message is the same spirit, division by zero. So I suppose we can understand what's happened here. And then if we want to see more details exactly where the problem is, that's where this traceback becomes useful. So we can see that the last part, which like it says here, the most recent call last. So that's actually the line that gave us the error. And we can see here that we have some line, which is return 1 divided by x, which is part of the f1 function. So each time it tells us which function this error has occurred in. So we then get the line number and the content of the line, and we get some context. So we get a few lines before and a few lines afterwards, so we can see where it happens. So we can see that in f1 we divided by x. So we may suspect that x was 0 when we called it. But to understand that, we need to understand like where this function was called from. So that's the time that we need to zoom out, to step out in this traceback, and see where f1 was called from. And we can see here that the context of calling f1 was inside another function, f2 in this case. And f2, as you can see in its code, you can see that it calls f1 twice. It gets two arguments, a and b. Once it calls f1 with a plus b, and the second time it calls it with a minus b. And you can see that the error actually occurred in the second time when we called with a minus b. Okay, and then we can again zoom out a little bit more, and we can see where f2 was called from, and that's already in the module. So that's like the main part. So that's where it was originally called. It was called here on the last line. We see that we tried to call f2 with 5 and 5. And then that sort of explains what happened. So we can see that by calling f2 with a equals 5 and b equals 5, then a minus b was 0. And then when we called f1 with 0, we divided by 0, and that explains why we got this error. Okay, is it clear for everybody? Okay. And yeah, and sometimes if we are not sure exactly why an error happened, we can just Google search, and very often we'll get a good answer. For example, here we tried to convert some string to an integer, and we got a value error, which in this case wasn't too informative. We see an invalid literal for int with base 10. What does it mean? We're not sure. So we can just take it and Google it and get a result. Of course, when we Google it, it would be better just to Google the part that we think is generic, and other people have encountered too. And it wouldn't make sense to Google everything, including this completely arbitrary number that I put. Of course, it could very well be that Google is smart enough just to ignore it and still give me a meaningful result, but it would make more sense to Google the part which I think is meaningful. So if I take it and do a Google search, then I open the first result on Stack Overflow, then immediately I get the answer that I should have used float conversion and not an integer because it's not an integer. And yeah, that's pretty much all I had to say about it. OK, so let's continue with talking about exceptions. So up until now, we treated exception as some kind of inevitable fate that we had no way of escaping from. But sometimes we could treat exceptions and actually carry on executing the code as if nothing happened, or to treat it in some other way and still carry on the code. So it's in fact our choice whether we want to stop the program when we get an exception, which is a default behavior, or we want to treat it in some way and carry on the program in some meaningful way. And the way we can do it is using this try syntax, in this case, try except. So the way it works is we use this try syntax. We open a block. Of course, we put a colon after the try, like every time we open a block. And then we can write whatever code we want to write inside it, which in this case, again, we try to take this number and convert it into an integer and then print something. So we already know that this should fail and we should get a value error. But this time, after putting the try, we put an except clause that tell us that we have some exception. And if we get a value error, like here, then we actually want to run this code. And then we can put whatever code we want, in this case, just one line of code. So what will happen is that Python tries to execute the code within the try clause. And then it gets a value error, and it moves to running the except clause instead. And we get an invalid integer without all of this mess of the traceback that we get by default. So, and if we want to put more code afterwards, then we can do it. We can put some more code, and it will continue to run as if no exception has happened because we caught it. We handled this exception. OK?
Can I just write an error?
Sorry?
I can do it with any type of error?
Yeah, any type. So in this case, we did it with the value error. But if you have a different type, you can specify a different type. Or there is even a way, I'm going to show you, that you can catch everything. It's not recommended, but you can do it. Yeah. OK, so it's important to understand that what's going on under the hood is that try actually just runs each line of code it runs until it gets the error, and then it just stops running and moves right away to the except clause. So in this case, the first line within the try clause will run because no error has happened yet. And then when it gets to the second line, that's the point where the error occurs, and then it will move to the except clause and will not run the last two lines. OK, and like I said, we may not specify a specific type of an error. We can just use a generic except and basically catch everything, which sometimes we want to do if there is too many things that could go wrong, and no matter what, we still want to catch it. But I really, really, really don't recommend you to do that if you have something more specific that you're worried about. So it's really much more recommended to catch a specific type of error. Because if you use the generic type, you may think that what you are catching is one type of error that you are expecting. But then in reality, when you run your code, you can find out that the real error that happens is something that you have completely unexpected. And for example, it could be some system error or memory error or something that you had no idea that could even happen. And then you will handle it as if it was some other kind of error, and it will be completely inadequate or inappropriate treatment of that kind of error. And nothing will make sense in your analysis anymore, and you might not even know that something bad has happened. So it's really not recommended to do it just carelessly. Now, we can also catch different types of errors, and each one can have its own except clause. And we can even treat them differently. For example, let's say that we have some function that gets a string and then tries to convert this string to an integer, and then trying to calculate its inverse, 1 divided by that number. So there could be many different things that could go wrong. So it might be that we don't give it an integer, maybe we give it a float, and then we'll get a value error. So we want to handle that kind of error, and saying that it was an invalid integer. Or it could be that we got a valid integer, but it happened to be 0, and then we get a 0 division error, and we want to say that we divided by 0. So it's a different treatment. And then at the very end, again, we may or may not want to do that. We can have a generic except clause treating all other kinds of errors, and we can say that we have encountered some unexpected error. So in this example, when we give 5, everything works fine. When you give it 13.3, then it's an invalid integer. If we give it 0, then we get 0 division. And if we try to give it a dictionary, then it's becoming an unexpected error. Any questions?
This is, in this case, not more informative. I would want to do something like this, just replace the invalid integer.
Yeah, I think, of course, it's not a real life example of how you might want to use exceptions. I think I'll have a more realistic example later on. This is just a toy example, just to illustrate what it does. I agree that in this case, it doesn't make sense to do any error handling. Maybe we just want to carry on. I think one reason we might still want to do it is maybe if some of the analysis fail, then we decide that it's not too bad. We just want to note what happened, maybe to write it somewhere, and then carry on to the next item to analyze. It could be, for example, that we try to analyze millions of sequences, and only say 20 out of those sequences fail. And in an ideal world, we would like to understand exactly why they failed and try to fix it and do something about it. But we might say, OK, we don't have time for that right now. It's only 20 sequences out of a million. Let's just ignore it. Let's just catch the error and note to ourselves that something bad happened, and carry on with the analysis. And maybe we'll treat it at some later point. It's a legitimate way to handle things. OK, there is one other kind of syntax that you might sometimes see. I think it's not very useful, but you should know that it exists. So the try except can also have an else clause, which is only executed if no error has happened. So that's actually the good part. So here we'll have something in try, and if something fails, if we get a value error, we'll get this line running. And if we had no error whatsoever, then the else statement will run, and we get this one running. OK, so this will run only if everything happened as it should have. And yeah, so the only difference actually between the else and line and just putting it as part of the try is that if we put it in the else statement, then it will not be subject to error handling in itself. So if we put it inside the try, then it could be that this line will also run and will encounter an error, and then it will be caught. But if we put it in the else statement, then if something goes wrong within this code, then it will not be caught, and we'll still get an error. So like I said, I don't think it's a very useful syntax. I think I cannot remember any time I actually had to use it, but it exists. Okay, so let's try to understand more what are these errors. And like everything in Python, like we said a million times, everything is an object, including exceptions. So these errors are themselves objects which we can work with. And the way we can work with them when we catch an error is within the except statement, we can specify the type of error, and then using an as statement and some variable name. And then we want to get the actual error object as a variable, which is called E in this case. And then this object, we can do all kinds of stuff to it. For example, we can use the str function to get the error message. So we can actually print the error message that we get. We can check its type and see that it's indeed a value error. And yeah, basically it. Okay. Okay, so we see that we can catch an error and handle it, and we can also raise our own exceptions if we want. That's actually a good design, and I encourage you to do that. So if you see that something goes wrong, instead of just ignoring it and continue with the analysis and hoping that something will fail down the road and the analysis will stop without giving you nonsense results, you can actually make some kind of controlled collapse of the program and say, okay, something is wrong here. I want to stop right now when I still understand what's going on and I can give an informative error message, and there is really no reason to continue the analysis. Or maybe someone else using this function will decide that they want to handle it in some way and catch this error or not, but that's a good stop point, at least with this function, to say that something has gone wrong. Okay, so let's see an example. So suppose that we have a function that takes one DNA nucleotide and converts it to an RNA nucleotide. So if it's a T, it returns a U. If it's an A or a C or a G, it returns the original nucleotide. And if it's neither of these options, then it's clearly not a DNA nucleotide, and we may want to raise an exception. So in this case, we can raise a value error and give some message to make it informative. So we raise a value error saying that it's an invalid DNA nucleotide and saying exactly what the nucleotide was. Okay, and then, for example, if we use this function using the map function, so we take some DNA, supposedly DNA sequence, and we use the map to run it on each one of the nucleotides to get it as an RNA, then we can see that when we run it, we get this kind of error. We see that we get an invalid DNA nucleotide U. So we didn't actually give the DNA nucleotide sequence, we gave it an RNA. And we get this error. Okay, so this happens right at the fourth time that this function is run. So the first, second, and third time it works fine. But then on the fourth time, we get this value error, and everything stops.
We don't avoid the error. It still happens. We can continue the code.
No, in this case, yeah, we do not handle it, so everything stops. But the benefit is that it stops in our own terms. So it's much more meaningful now what exactly has happened. Whereas if we just ignored it and then ran some more analysis, something could have gone wrong only, I don't know, 100 lines of code later and half an hour of analysis, and it would be just a waste of time and efforts to then try to debug it and figure out what happened. Okay, and of course, like any error, when we use our own errors, we can try to catch them. So here we have a try and except clause, and we catch any exception now is E, and then we print what we saw. Now, when you raise your own kind of error, it's better to raise a specific kind of error. So for example, if it's something wrong with the value that you get, it's better to raise a value error. And there is a list of all the kinds of errors. You can look it up in Python and see if something appears to you to be more appropriate. But if you do not see any kind of specific error that makes sense to you, then you can just use the generic exception. Again, it's less recommended, and in a future class, we're going to see that we can, we'll talk a little bit about how to write our own classes, and we can see that we can write our own exception types, but for now, we can just raise a generic exception, and this will also work, and just stop the execution. I will also say that sometimes it can be useful for debugging, especially in Jupyter that doesn't have any special debugging capabilities. So in some debuggers, for example, we can add breakpoints. So we can specify that we want to stop the execution at some point. In Jupyter, we do not really have this feature. So for example, if we have a loop inside a loop, and we want to execute, we want to stop the execution after some code is run in the inner loop, using a break statement, for example, will not help because it will only stop the inner loop. It will not stop the outer loop. But if we just raise an exception, again, without any arguments, just for debugging mode, then it will stop the execution right here and now, and nothing will continue to run. So it will run this code just once and then stops. So it could be useful for debugging if you want to run just part of your code and you don't want to execute the downstream analysis. Then you can just use exceptions to stop everything. OK. So I now want to speak about the finally syntax. So let's start with a quick motivation. So suppose that we open a file in writing mode. And then we want to write something to it, and then we close the file. OK, so suppose that we run it, and then we encountered an error. So something went wrong, and we got this value error within this for loop. OK, so we get errors all the time. It's not that bad. But there is something bad that has happened here. And that is, if we look at the status of the file, we see that it's not really closed. So the fclosed attribute is false. We thought that we made sure to close this file because we had a close at the end, but we didn't take into account the option, the scenario in which we would get an error, and then this close statement would not even be executed, and the file would remain open. And that's bad, especially if we work in writing mode. So we want some way to make sure that even if something bad happens in our analysis, we still make sure to close the file. So one way to do that is using the try except syntax, like we saw earlier. And we can have a try statement that runs the analysis and then tries to close the file. And if something happens, we can assume that the file wasn't closed and still close the file and then re-raising the exception. So this will, on the one hand, still give us the exception because we re-raise it after we catch it. And on the other hand, we can see that this time the file is closed for certain. So it's a way to do it, but it's a somewhat ugly and not very convenient way to do it because there is all of this messy try except syntax, and we need to do the close twice. And it's not even entirely certain that once we get here, we're not sure whether it was closed or it wasn't closed. A better way to do it is to use something that is called the try finally syntax. The way this works is instead of a try except, we just have try and finally. So like in the try except, everything within the try clause tries to run. But then whether we get an error or we don't get an error, it doesn't matter. No matter what, everything within the finally clause will be run. And we indeed close the file. But then we still get the error because we didn't catch it. OK? So what happens in Python is that it runs everything in the try. It gets an error. And then right before it throws the error at us, it will first run the finally clause and only then raise the exception. So we still get the exception, but we still have that the file is closed like we wanted it to. So the try finally is very useful syntax if we want to make sure that something runs even if we get an error. It's especially important when we use some kind of resources like files, and we want to make sure that they are closed no matter what we do.
What is the difference between accept and finally? They both do it after the error.
Yeah, so, but there are two differences. So first, the accept clause will run only if there was an error. If everything worked smoothly, it wouldn't run, whereas the finally would run no matter what. So if we did an accept and then close the file, it would close the file in case that something bad happened. But on the normal scenario that nothing bad happened, we would still have the file open. And then another difference is that when we catch an error, we catch it. Then we don't longer have it, and the execution will continue after the try except statement. Whereas if we use finally, the error will still be raised, so it doesn't interfere with the mechanism of throwing the error. And we can combine the two kinds of syntax into one try except finally statement. And of course, we can add as many excepts as we want within this statement. So we can try executing some code, and then if something bad happens, we want to handle it in some way. But there is something that we want to happen no matter what, and we put it inside a finally. And you can see that here we got this error, and we still got the file closed. Questions? OK. So the try finally was a nice way, a better way to work with files and making sure that they are closed. But now I want to show you an even better way, which is actually the recommended way, that if you see code examples online, you'll see that most people use this option. And that is with what is called the with statement. So we saw that we could open a file, try to do something with it, and then finally make sure to close it. Another way, which is even shorter, is to use the with statement. So here we open the file as part of this with statement, and we specify the variable name for this file that we opened using the as statement and then the variable name. So we open this file, calling it f, all within this with statement. And then everything that is within the with statement will be executed with the file open, but everything outside the with statement afterwards will be with the file closed. So what it basically does, it makes sure that the file is open as long as the with block carries on. And once you leave the with statement, then it will make sure to close the file, and it will also make sure to close it even if some error happens. So even if something bad happens here, you will still have the file closed. Actually, the with statement is more generic. So it allows us to, it's called, in the Python community, it's called the context object. It allows us to create those kinds of types of objects which have a context, like a file, that we want it to be open just within the with context, and outside of this context, we want it to be closed. And we'll see more examples of that later in the course. But by far, the most common use of this syntax is with files. And it's indeed a very convenient way to work with them. And that's the way I recommend you to work with files from now on, using this with statement. OK, questions? Yeah.
If I assign a variable in the with statement, it will be exist outside?
I think so. Yeah, it's like a for statement or a while. So it's not like I think the only exception of that is functions, which have their own set of variables. So when you work within a function, it has its own kind of context and environment, and variables that you define within the function will not exist outside the function. But in other kinds of blocks that we see in Python, in if statements, in loops, in with statements, then all variables exist as if there were global variables. Yeah. Okay, and finally, let's talk a little bit about validation of code. So like I said, if you see that something is wrong, it's a very good practice to detect it ahead of time and to throw an error, and not to allow yourself to continue the execution of the program with something that is clearly invalid. So for example, if we create a function that we want to extract some subsequence out of the sequence, so we give it some sequence, and we give the start index and an end index, we may want to validate that certain assumptions hold, that if violated, the analysis wouldn't make sense. For example, if we give such a range, we expect the end index to be larger than the start index. So if the start is greater or equals to end, we want to raise a value error saying that start must be smaller than end. And we also expect that that the start will be the start will not be negative, and if it is negative, we say that it must be positive. And we may want to make sure that the end doesn't exceed the length of the sequence. And if that happens, we want to throw another value error saying that it's not right. And only if all the validation steps have been validated, only then we want to actually execute the code and run the analysis. And we can see that when we use it, so the first time it's fine, we give it 3 and 5, which are valid indices, but the second time we give it 3 and 2, and we get this error that the start must be smaller than end. So I really encourage you to do this kind of error checking within your code. I think it can really spare you a lot of problems and hard debugging down the road. So that's one way to do it, just to use if statements, and if something is wrong, to raise an error. There is an even better way to do it, and that is using the assert syntax. So in the assert syntax, we can do everything in just one line of code. Basically, the way the assert works is it just gets a Boolean value. And if this Boolean is true, then it does nothing. And if this Boolean is false, then it will give you an error, and you may specify exactly the error that you want to get. So the way we work with it in practice is we specify some kind of condition that we expect it to be true. And if this doesn't hold, then we'll get this error, and everything will stop, and we'll get what is called the assertion error. OK, so the assert is much nicer than the kind of syntax you see here, I think for 2 main reasons. First, it's shorter. It's just 1 line instead of 2 lines. And also, in the assert syntax, instead of specifying the negative condition, you specify the positive condition. So you specify what should happen instead of what shouldn't happen. And I think sometimes it's much more intuitive, because you can actually specify all the assumptions that you expect to be respected in this example. So instead of asking whether a start is greater or equals than end, which is the negative condition, something that shouldn't happen, you ask whether a start is smaller than end, which is what should happen in this case. And again, highly encouraged, and the more you do asserts in your code, I think it will be easier for you to maintain and to debug it.